For mathematics, we're going to talk about basically two things, two or three. So the first thing is something called vector and tensor analysis. So that's the first thing. And the second thing is something called notation, because when we write things, we can write things in different ways. So notations, just different ways for writing mathematics. And the third thing is the partial differential equations. So let's go to the first thing. And for tensor and a vector and tensor analysis, actually the vector is one type of tensor. So we can use tensor analysis to represent all of them. So we're going to talk about a vector analysis first. So we will start from the easy one. And then we will show how to move from vectors to tensors. And so So vector analysis. So for vector analysis, we have, someone is outside? No? Okay. Objectives. So for objectives, so you need to know, you need to understand and write vectors. Second, so you need to operate. Let's use another word. Let's use handle the basic operations and calculus of tensors. Then for contents. So first, let's first try to understand tensors based on our knowledge on scalars. Vectors. So again, now we are talking about math, right? And math, again, is the language of multiphysics. That's why we need to know about it, because only when we know the basics mathematics that we need for multiphysics, we can talk about it. We can write mathematics, and we can communicate mathematic problems using the language. And also, there's another thing that we need to recall before we talk about vectors. That is field. Or to be more specific, physical field. So do you guys still remember what's the meaning of physical field?
In every in every situation, or for example, in X, Y, Z, we have a amount for
value,
example, for temperature. We have this temperature everywhere in this room.
Yeah, that's good. It's actually, it's just spatial distribution of a dependent variable, not a dependent, a state variable, right? We say there are different types of variables, but we want state variables, which is not related to the properties of materials, and it can be used to represent the status of the current system. So for the definition of fields, we know that there are two things. First, we need to have a state variable. And second, we need to have a spatial coordinates. So spatial coordinates, another word, the word that is corresponding to spatial is temporal. Temporal means time. Temporal will also have temporal coordinates, that's the time. So spatial coordinates, depending on what space you're talking about. For example, in the common Cartesian coordinated system, we're talking about x, y in 2D and x, y, z in 3D, right? So those are the spatial coordinates. So the definition of a field is that, for example, here I give out one example, that's the temperature distribution. So assume that this is we use the word domain to represent the area of the object or system that we want to analyze. We said that inside domain is omega, and the boundary of it, sometimes we use delta omega, or sometimes we use this symbol to represent it. And the definition of a field is that within this domain, at every point we have a value for a state variable. For example, T, temperature. So we move to a different point, we also have a T value. It may be same or maybe different from the value at this point. So this is the variable, this is the field. And in numerical analysis, because we don't consider a continuous space, so we only have grid points, and they are apart from each other. So we're gonna have T, then define usually at these grid points, and sometimes at some other special points between them. But we can understand that it's not continuous. That's what we discussed. And this is the definition of, and we know that for the state variables, the reason that we want to discuss vectors and tensors, the reason is that in the example that I just gave, you can see that the state variable T is we just need to use one value to represent it at one point, right? But let's go to another example. If we don't have two, for example, if we have v velocity, then in this 2D case, how many numbers we need to use to represent the v at every point?
Direction and also scalar.
Yeah, but at least the answer is 2, right? And we can represent this v in two ways. For using different coordinate system. For example, we can use x, y, or we can use the magnitude and angle, right? They're different ways. But anyway, now v cannot be represented using just one value. We need to use 2, right? So what we just did is that t here is a scalar. Make sure you know how to write it and how to pronounce it. It's S-C-A-L-A-R and a scalar. And v here is a vector. So what happened is that if we have T, is here temperature, we just need to have one value. For example, if we use Kelvin, let's say that is freezing point, then 273 K. right? And this one, if we use the language of tensors, this is also tensor, but it is 0th order of tensor. So tensors, could have different orders, and a scalar, just the order is 0. And if we move from T to V, and in this class, so if I want to usually I put an arrow above a symbol. If I do handwriting, I will put an arrow above a symbol to indicate that this is an arrow. And V in this case, we know that it could have two values, for example, x and y. Let's say, for example, 5 meters per second along x and 3 meters per second along y. And in this case, we use a 1D array to represent this V, this field. And this is the first order of tensor. So you can see that scalars and vectors, they're just special cases of tensors. And if we can also, even go from vectors to tensors. Actually, we'll discuss this later. But here, let's try to find one example. So, is there any example? Could you guys think of any example which could be more complicated than velocity and a state variable, can be distributed at different points? So if again, this is a very classic example. If I sit on the table, so I will cause something. Deformation. Deformation is good, but deformation is like a x, y, z, so it's still a vector, right? Is there anything that's more complicated than like x, y, z? Sit on it, I cause but stress. Tensor, just one type of stress. And in stress, we know that some of you possibly still remember. So here, again, first for stress, use sigma. And I prefer to put a bar above a symbol to represent that this is a second order or second or higher order tensors. So for sigma, we know that it can be represented using something like sigma 1, sigma 1, sigma 1, 3.
Yeah.
Does this ring a bell? Right? This is now it's like a two. It's like this is like like now we have a 2D array or a matrix in this case. So sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 1, 3, sigma 3, 1, 3, 2, and 3, 3. So in this case, this is second order. If we keep going, we can get tensors with even higher orders. But the problem is that if the order get higher, it's kind of hard to visualize it. Just for example, if we can easily visualize 3D space, but when we move from 3D to 4D, it's hard. We cannot do that. But they exist. So this is why we need to talk about vectors, because for multiphysics, we want to talk about the physical field. And the physical field, we want to focus on the spatial distribution of state variables. And for state variables, some of them they're scalars, some of them vectors, some of them are more complicated. They are higher order tensors. So this is the reason. And second, let's talk about there's a few more things that we want to know about. So first, for a scalar, the thing is that a scalar does not change with the coordinate system that you choose. No matter what x, y, z that you choose, right? The scalar, this is at any point the value stays the same. For example, at temperature at this point, no matter you use that as the origin point and set x, y, z there, or you set x, y, z at the another corner of the classroom, you will get the same value for temperature at this point. But for v, velocity, actually v does not change either. The vector does not change. However, the projections of the vector to the x, y, z, they will change. It's just like you have something in there, and if you look at it at different angles, it will appear different to you because you choose different angle to look at that object. It looks different. However, the object does not change. So the vector itself does not change. However, the representation of the vector or tensor, they will look different. If you choose a different coordinate system. So that's another thing that we want to know about vectors and higher order tensors, scalars and higher order tensors. And after we know about vectors, I know that for scalars, actually we know how to deal with, how to handle scalars. For example, there's just one number, right? For one number, we know how to operate, a single number. We have something called addition, subtraction, multiplication, right? Division. That's the basic operations of with scalars. We learned that when we were at the elementary school, and then when we get to the middle school, high school, we learn more complicated things, right? We started talking about more complicated operations, something called calculus. Maybe at the college, we talk about differential calculus and integral calculus, right? So that means we know how to deal with scalars. So now what do we need to for scale vector analysis? What do we need to know? What we need to learn is that we want to learn how to deal with vectors and higher order tensors, just like what we did with scalars. So those basic operators and the more complicated calculus. So we need to know those things for vectors, and that's what we're trying to do today. So for the operations, so what do we want to know how to deal with? And we have two types of, we have basic operations. And when we talk about basic operations, we have something addition, subtraction, multiplication, and division, right? And for this, we have, if we are talking about the basic operation of scalars, actually, that is the study of arithmetics. And if we are talking about the vectors, actually we also learned something about basic operation of vectors in the high school or at the college. And that is vector algebra. So what we learned in linear algebra is closely related to the vector algebra that I put down here. And for the vector algebra, you will also have, first you will have something called scalar multiplication. So that is just multiply a vector with a scalar with a vector. And we also have, other, for example, addition, subtraction, but we don't have multiplication anymore. Instead, we have something called a dot product and a cross product. So these are two new things that we're going to learn today. So pay attention. So these are the basic operations. And in addition to the basic operations, there's another big category of the operations with vectors and higher order tensors. So those big category of operations are usually used to describe the change of state variables. They're not talking about the basic operations, talk about the change. And for the change, we also have the change of scalar. So that is what we learned in calculus. And the change, then the change of vector. Then you're going to see something like this. Oh, first, this is vector calculus. And for this one, you're going to see operators like this, like this, like this, and like this. So those are kind of the fancy things that you possibly have seen in the partial differential equations of when we are talking about multiphysics. So you can see that. So we did multiphysics before, right? Arithmetics before, right? When we are at the elementary school. And for vector algebra, we learned a little bit when we are learning the linear algebra. So this is the thing we learned a little bit, but not too much. So we're going to talk about it today. And for calculus, we did this at college. And for vector calculus, we never talked about it before. So that's what we need to cover in this course. So then let's move to vector algebra and vector calculus. So one is about the basic operation, the other one is about the change of vectors. So first, let's talk about vector algebra. So again, this is about the basic operations of vectors. And we need to talk about different operations. And the first operation that we want to discuss is that scalar multiplication. So scalar, okay, before we move into this, so let's do another thing. Apologize. Let's talk about the notation first. Let's write, apologize. Let's talk about the notation of vectors. That is how we write vectors. So we can write it in different ways. So for example, the comprehensive way the tensor way is that, we just write it like this. This is the tensor way. And if we want to write it in a comprehensive way, then vector v is depending on you're talking about 2D or 3D. So let's talk about the 3D space. Usually we say v I or xyz. We can use ijk or xyz. So v I e I. So you can see that E has a arrow above it. That means it's a vector. Plus Vj Ej plus Vk Ek. So what we did here is that actually we project the V to 3 coordinates, to the 3 axes. And VI, EI is just the projection of V along the I-axis. But here, I put an arrow, above EI. That means this EI is a unit vector. So for EI, the meaning is that, let's write down here. So let's say this ijk. Usually we need to, the ijk need to follow, the right-hand rule. That means if we rotate from I to j, and then this k this direction of the k need to the direction of thumb. This is the right-hand rule. So what we do is that here we have a vector v here. So the reason that why we can write it in this way is that we project this v onto the 3 axes. So we will get 1, 2, and 3. So the magnitude, for example, of this one is vi, and the projection, the magnitude of the projection on the k-axis is vk. But it's a magnitude, so it's not a vector. So the meaning of ei, ej, and ek is a unit vector. So the magnitude of it is 1, and it has a direction. So this one is ek. And the ek, for ek, the magnitude of it is 1. And the direction is along the k-axis. So you can see that what we did is actually we split one vector v into 3 vectors. And they have prescribed directions, and the magnitudes depends on the projections of this v onto the 3 axes. So this is the comprehensive way. And we can also use, the matrix or arrays. So let's use array. So if we use array, sometimes we do it in this way. We say that it's just Vx, Vi, Vj, and Vk. So we just use the projections of this vector onto the 3 axes. We put them as an array, write them as an array, and we use this array, 1D array, to represent this V. This is another way. So there are 3 ways. Actually, there's one more way, it's a little bit more complicated. Sometimes, some people prefer to simplify this comprehensive notation of writing, for writing tensors. They say that, the comprehensive way can be written as, so this is the array notation. So for the comprehensive way, we have for example, it's Vi, EI. Right? And here we have a summation sign here. This I, for example, if it's a 3D space, means from 1 to 3, or from X to Z to X to Z. Right? So some people prefer that, they want to omit this summation sign. So they introduced something called Einstein summation convention. They said that as long as we have two identical subscripts, for example, in this case, we have I as a subscript of V and also has a subscript of E arrow. So in that case, we can just write it in a simple way as. So if somebody write it, something like VI, EI arrow, and you say that we follow the Einstein summation, that means this is a summation. So that's something, a lot of people will accept. So these are, 4 things that you will possibly see for notations of tensors in this course. And we know the notation of vectors. Then let's move to the vector algebra. For the basic operations of tensors. And the first operation that we want to know about is scalar multiplication. So scalar multiplication is straightforward. It's just multiply a vector by a scalar. So in this case, alpha, so there's no arrow above it, there's no bar above it. That means is a scalar. And the meaning of this scalar multiplication is scaling. So that is, kind of straightforward. Scaling, that means, for example, if just like if it's just a one line, if we're talking about scaling, for example, we have to scale it by 2 times, that we prolong line, from the original length to 2 times of the original length. That's scaling. And what happens if we use some other notations to represent it? For scaling, so if you use vector notations like this, if we use comprehensive notation, what happens is that we just multiply all the components of the vectors. So alpha EI plus alpha VJ EJ plus alpha K EK. So you can also write down it in the other notations. For example, if we use the array notation, it's alpha VI, alpha VJ, and alpha VK. So that is scaling. And if we want to use let's use a 2D example, X and Y, or I and J. Let's stay with IJ. I and J. For example, we have the variable V. And what happened is that for scaling, we just prolong this vector, or we shorten it using a specific scaling factor. So this is the original one is V and the one that we obtained here, this is alpha v. So it's also a vector, and the direction does not change. We just change the magnitude. So this is the first basic operation. Second one, addition. So for addition, it's written as, for example, now we have, let's say, we have two vectors. We have u, vector u, and vector v. And addition, for the addition, we add them up. And what happens is that if we use a plot, it's look like this. For example, let's assume that VU is like this, and V is like this. Do you guys know how to get V plus U plus V? You should have learned it somewhere else, right? So it's actually, we just need to draw a parallelogram, forming by this U and V vectors, and U and V is just this, the diagonal. So this is U plus V. And if we want to write it using the comprehensive, let's do not do the comprehensive way. To save space, let's use the Einstein summation. So we will use the Einstein summation, or let's just keep this. So what happened is that is UI plus VI, then EI. And again, the 3D space, I goes from 1 to 3. And if we want to talk about, want to use the array notation, again here, which is U1 plus V1. That's the first element or entry of this array. So the second element is U2 plus V2, and the third one is U3 plus V3. So this is addition. And subtraction, actually, we can get a subtraction based on the definition of addition. They are closely related. So here, let's write it here. So for subtraction, we also have, V, U, and V. Then what is U minus V? Yeah, from the end point of V to the end point of U. So this is U minus V. Right? So you can define it in the same way using the. So here's U minus V, and here we use UI minus VI, then along the I direction, and also here is U1 V1, U2 V2, and the U3 V3. So this is subtraction. And next, something that's a little bit new to you. I think you should also learn this some before, but possibly not in the way that we present this. So the next one is something called dot product. So when we are talking about scalars, sometimes when we say it's the product of two things, we can write it in multiple ways. So let's give you an example. Just u. So you were talking about scalars. So we said that a product of u and v, we sometimes just say uv, or we can say u dot v, or we can use the multiplication sign u plus v, right? That's how we deal with scalars. But now for vectors, we cannot do this anymore. They're not the same thing. So when we go to vectors, this is what we did with scalars. So for vectors, uv is not equal to u dot v. Not equal to u cross product v. They're not identical. They're totally different. So pay attention to this. That's why we want to talk about vector analysis, because the operations of vectors, they're different from the operation of scalars. They're more complicated. Vectors, the operation of vectors is just a special case of the operation of tensors. So now for dot product, so it's just like the dot product of u and v is u dot v. And the meaning of a dot product is actually, here I just write down the meaning of it, is something called projection. So let's say that we have a dot product of u and v here. So this is u and this is v. Then the product of u and v is just the projection of v on u, or the projection of u on v. In this case, let's say this is the projection of v on the direction of u, right? So it's a projection. So this needs to be a right angle. And here is u product dot v. It's a projection. That means it's a scalar. So now you can see, one thing that we need to pay attention to is that the dot product of two vectors, two first-order tensors, will be scalar. So you can see that this operator changes the dimensions of two vectors on two sides of it. So that's what we need to pay attention to. That's the meaning of it. And sorry, I forgot to mention a few other things. So when we are talking about different operations or different operators, one thing that we need to know is the rules of using these operators. For example, when we talk about the rules, we have something called commutative. That means whether we can change the position of two variables. For example, for this one, could we change the position of u and v? So that's kind of one rule. That's called commutative. So if we can change the position, we say that, okay, well, this operator is commutative. And we have something called associative. Associative is that when we have, for example, u product of the addition of another two products, could we associate u with with two of those variables separately? So that is associative. And we also have I apologize. That's not associative. That's distributive. So let me use scalar product. Use this one, scalar multiplication, to show the rules. So for example, first for C, actually, one easy way to remember things is, we can call it CAD here. C is commutative, A is associative, and D is distributive. So C, let's see if it's commutative. So for C, that is alpha V, whether alpha V equals V alpha. Actually, we can prove it, based on the definition here. For example, if we use the comprehensive notation of it, based on the definition of scaling, we know that commutative, this operator is commutative, and is also associative. So for example, alpha beta V, this one equals alpha beta V, and it's also distributive. So in this case, alpha U plus V equals alpha U plus alpha V. So this scalar multiplication follow all the three basic rules. And for addition, follows commutative. This one is easy to understand, so we don't want to spend too much time on it. So let's focus on dot product. So this one is a little bit more complicated. So first, for C, commutative, let's just write down C here. Actually, C for dot product is good. So that means the product of UV equals the product of VU. So this one is easy to understand because, no matter it's V dot U or V dot U, they can be understood as projection of V onto U or U onto V. They're equal. And associative, no. Because usually we don't talk about whether this dot product is associative or not, because you guys can see this. For example, if we have three vectors, U, V, W. U, V, W. You will see that this one is not valid. Why? Because let's take a look. The dot product of U and V is going to be a scalar, right? Between a scalar and a vector, there's no product, dot product. So it's not valid. That's why we don't have associative law, for the dot product. But for distributive, this one is good. So we have dot product. For example, if we have U, dot product of U and V and W. So this one equals U, the product of UV plus the product of UW. So this is the rule for using a dot product. So we need to know the definition of it, and also need to know how to use it. And next, cross product. Oh, another thing, actually, before we move to cross product, for dot product, it has another name. It's called a scalar product. The reason is that, by doing this operation, we can obtain a scalar. And the cross product is called a vector product, because the cross product of two vectors will be another vector. So first, write down cross product is U, the cross, and V. So this cross is just like the multiplication sign that we used when we are doing when we are multiplying two scalars. And for this one, first, let's take a look. What's the meaning of it? The meaning of this cross product is actually like this. Let's say we have U along this direction. We have V in this direction. Then the cross product of U and V will give us another, this U and V vectors will give us another vector along the direction which is normal to the surface formed by U and V. So let's say if the U and V, they're just like here on this surface of this piece of paper, and W, so the cross product of U and V gonna be this direction. So it's normal to the surface. And also to determine direction, we need to use the right-hand rule. Says that if it's U cross product V, what happens is that you need to rotate from U and V using your fingers, and then just take a look at the direction of the thumb. That's going to be the direction of the cross product of U and V. So in this case, W is normal to the surface of U and V. This is W. And this is the direction. What about the magnitude? Actually, the magnitude of this W is just the area. So the area is just the magnitude of U plus V. And if you want to write down, how to use symbols to write down, the U plus V. Actually, it's gonna be like this. So U plus V is gonna be equal to the determinant of the following matrix. So this means determinant. So this EI, EJ, and EK. And here we have UI, UJ, UK, and VI, VJ, VK. So this is the simple way to write it down. And do you guys still remember how to calculate the determinant of a matrix?
Yeah. EI multiple to...
Depending on the direction, right? So if we go, for example, this direction, here, it's going to be positive, right? If we go this direction, the other direction is going to be negative, right? So let's do it in this way. So it's like, first, start from here. UI, VJ it's going to be EK, right? And this, because go along this direction, so it's going to be positive. And then second, UJ, VK, and it's going to be EI, also going to be positive. Then plus UKVI, and EJ. This is also going to be positive. So then we need to go along the other direction. It's going to be minus. So it's going to be UI, VK, EJ. Then minus UJ, VK, sorry, apologize. UJ, VI, EK. Then minus UK, VI, EI. So that's, and you will see that now, this is the addition of several vectors. So vector, 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 we add them up, we still get a vector, right? So in order to simplify this, some people introduced some additional operators. For example, let's talk about first. So we are supposed to introduce this later. Okay, let's do it later. So let's first just stay with this one. It's a little bit complicated, but at least you know how to write it. This is the dot. This is the cross product. And for the operation, the rules with the cross product, first, for C, one thing we need to remember that is not commutative, but instead is something called a counter-commutative. So for C, we have so we add a counter here. That means the cross product of U and V is the negative of the cross product of U, V, and U. So that's the meaning of counter. So we have a negative sign here. And for A, actually, it's not associative. It's not associative, but instead it's actually a little bit more complicated. Usually we need to use some other more advanced tools to take care of, if we want to associate, put different different vectors on two sides of a cross product operator together. We want to use some other thing, more advanced tools. For example, use the Lagrange's formula. So we will talk about this later, and something we'll also use Jacobi's identity. We use these tools to handle, if we want to associate different vectors on two sides of the cross product vectors operators. And D, distributive. This one is valid. So for example, if we have U, the products between U and addition of V and W. So this one equals U cross V plus U cross W. So and there are two more things. We have something called scalar triple product. For scalar triple product is just, so first it's called a scalar triple product because if we use a scalar triple product, we're gonna get a scalar, and it's defined as a compound operation with both vector product and a scalar product. So it's U dot, then the cross product of V and W. And this is one of them. Another one is called a vector triple product. And this one is defined as U cross the cross product of U V and W. And we know that the cross product of two vectors will be another vector. So here, this vector, and another cross product. So we will also get a vector. So that's why we call it vector triple product, because it will give us a vector. And for both of them, if we want to know the rules, it's pretty complicated. So we need to refer to some identities in vector analysis. And we will do that later.
I think I'm falling for you.